I and 2,999 other people.
Then you're also my grandfather.
Yes, right. Grandfather. Who is your advisor?
My advisor is Craig Chambers, or great-grandfather, sorry.
Yeah, that's right.
Yes.
Considerably older.
His own chair.
Okay, you know what, maybe we'll start with this.
Sure, that would be great. I was not told about the 10-minute allowance, so my talk is probably closer to an hour than 50 minutes.
That's fine.
Okay,
When there's nobody left, then you know it's time to stop.
perfect. I'll just keep talking until everyone leaves.
Okay, so let's see, I need the mic.
That's right there.
There we go. So it's a great pleasure to introduce Jeff Dean from Google. Jeff just told me that he's been 19 years at Google, which makes him one of the first employees. In fact, he's employee number 19 at 219.
20-something, yes.
Oh, 20-something. Okay. Okay, and that's so that's really quite excellent. And he is now a Google Senior Fellow, and he's responsible for many of the things that we use, including, if you're there early enough, crawling, indexing, query serving systems. These are all things that are part of everyday life. So that's terrific. And a number of other very important things at Google. He got his PhD from University of Washington, and he is bachelor's from Minnesota, but he has some very high honors in our field. He is a member of the National Academy of Engineering and the American Academy of Arts and Sciences, and a fellow of the Association for Computing Machinery, and on and on and on like that. So with that, let's thankfully welcome Jeff with some applause, because we use his stuff every day.
Cool. All right. And is that on? Can you hear me? Okay, great. So I'm going to talk to you today about the use of deep learning in solving a bunch of different problems around many different areas of application. And I'd like to point out this is not purely my work. This is work of many, many people at Google, some of which I'm involved in as a co-author, some of which I just think is cool and I want to tell you about. First, let me tell you about how Google sort of approaches doing research. So we have a large number of researchers in many different offices around the world. We're very excited that we're opening an office in Accra, Ghana later this year. In part, the way we focus on doing research is 4 different sort of flavors of research. The first is sort of basic research that we think is a set of interesting problems that we want to try to tackle, and that if we were able to solve them, would have impact in allowing us to do new things that we aren't able to do today. A second flavor of work that we do in our research organization is we build infrastructure to enable us to do this sort of research, and also allow the research that we do to then be widely utilized by both people inside Google and outside Google. Building infrastructure, things like TensorFlow, which is a machine learning open source library that we've built. We also do collaborations with various Google product teams to get research ideas out into real product uses. So things like Translate and Photos and Search and Ads and Gmail have all had sort of extensive collaborations over the last 4 or 5 years with various parts of our research organization. And then we also conduct research that is applied to new or emerging areas that Google doesn't currently have products in. So a couple of good examples of this are machine learning applied to healthcare-related problems, and also machine learning for robotic control. And I'll talk about most of these things today. Since I'm at a university, it's also important to highlight some of the ways that we interact with the academic community. So for those of you who are faculty, we have a pretty comprehensive faculty research award where we can find researchers who are interested in similar problems to some of the problems your own faculty are interested in, and people can apply for grants to support graduate students and things. Focused awards are sort of larger versions of those, and we have various visiting faculty and so on. And for students, we have a wide variety of different ways of interacting. We have lots and lots of internships that we host every summer mostly, and also throughout the year, residency programs and so on. So you can learn more about that at that URL. But the interesting thing in the world in the last 8 or 10 years is the growing interest in doing machine learning research and the kinds of problems that we're able to tackle using machine learning. So this is a graph showing the growth in machine learning related papers posted to Archive, which is a paper preprint hosting service. And that red line there is the exponential growth rate that Moore's law got us accustomed to in computing performance for many, many years, about 40 of the last 50 years, although it's sort of diminished in the last 10 years, of doubling every 2 years. And so we're essentially seeing a higher rate of growth in machine learning research than we were seeing in computational growth for the nice duration that Moore's law gave us. So we've sort of replaced higher performance computing growth with machine learning research idea growth, which is a good thing. And deep learning is this kind of modern rebranding of actually a set of ideas that have been around for about 30 or 40 years of artificial neural networks. Basically, these systems that can learn in this layered fashion to learn deeper and deeper layers of abstraction from fairly raw forms of data. And they can be trained end-to-end with gradient-based methods. And they can learn from many different kinds of heterogeneous and noisy data to do interesting things. And one of the nice properties that these systems have is that you don't need to do as much explicit feature engineering, because these systems can learn to build on abstractions that are learned in the learning process and develop their own internal representations of higher level features. And we've seen over the last 4 or 5 years that deep neural networks can actually do very powerful things across a bunch of different domains. So one of the most interesting areas is the use of neural nets for computer vision has made great strides. So you can take in the raw pixels of an image and produce as an output a classification of even fairly fine-grained classifications. So if I looked at that, I would say monkey, because I don't know very many monkey species. But given the right training data, you can actually train these models to do very fine-grained classification of things like 10,000 or 100,000 different categories of objects. You can take in audio waveforms and produce transcripts of what is being said, how cold is it outside, essentially learn a speech recognition system end-to-end purely by observing these kinds of inputs and outputs. We can take parallel language data, so sentences in English and French, say, and learn to take as input a new English sentence, hello, how are you, and produce as output the corresponding French sentence, bonjour, comment allez-vous. And we can also take pixels and do not just classification output, but actually produce simple sentences that describe that image. Some of this work was done contemporaneously at Berkeley. There were actually 4 or 5 research groups around the world that are in the same month or two realized that this was going to be an interesting approach and generated these caption generating models by fusing essentially simple language models with computer vision models for classification and developing models that could actually emit simple sentences like this. And so that's actually showing some reasonable level of interesting understanding of that scene. It knows that train is blue and yellow, that trains typically sit on tracks, and so on. And so in vision, for example, the error rate in the ImageNet challenge has gone from 26% error the year before people started using neural networks for this, for a task where human error is about 5%. And in 2016, the error rate was actually 3%. So substantially better than human error rate on this task. Although this task is a bit esoteric, you have to distinguish 40 different breeds of dogs among 1,000 different categories of things. But we've gone from basically computer vision not working very well to now it actually works well enough that we can actually rely on it for tasks that we didn't used to be able to rely on it. And that's a pretty big thing. If you think about where we are in computing, computers can now see, and 5 or 10 years ago, they weren't really able to see very well. So the rest of the talk I'm going to structure as a tour around how some of these basic developments in deep learning are going to affect a bunch of different areas in computing and beyond. And in 2008, the US National Academy of Engineering got together a group of experts to think about what are a bunch of areas that should be grand challenges for different scientific fields for the 21st century. And they came up with this list of 14 different topic areas that they thought were really important things to focus on for, in theory, the 100 years, but they waited 8 years, so 92 years for the 21st century. And I actually think if you look at all of these, machine learning is going to be helpful in solving all of these to some extent. And obviously, to some, it will be vital. To some, it will be perhaps an important component, but not the only component. And within our research organization, we actually have projects looking at how to use machine learning to help all of these things that are listed in red. And I'm going to be talking mostly about the ones that are in bold-faced red today. So that's sort of the tour of the rest of the talk. So one of these grand challenges is restore and improve urban infrastructure. And it's pretty clear that we're on the cusp of a development that's going to really change how we think about urban environments and how we design cities. And that is the development of autonomous vehicles. This has been an idea that's been around for quite some time, but it's only through the development of better perceptual techniques that allow us to take raw forms of data that these autonomous cars are collecting from many cameras on them, radar data, spinning LiDAR data, that gives you raw inputs about what is the world around this car looking like, and fuse these together into a high-level representation of what are the different objects around this car, how are they likely to behave, what are they, is that a solid object that's not going to move, is it a pedestrian, is it another car, and so on. And so deep learning is really key to making autonomous vehicles work, because once you have this representation of the world, you then want to be able to figure out what are the set of actions I want to take in this world that are going to be safe and that will accomplish my goal of getting from A to B without actually having imperiled anything. And just to give you a sense of where we are in this, Waymo is Alphabet's self-driving car subsidiary. And they've been driving more and more miles, and the miles that they've been driving in these vehicles have been growing quite substantially. I think the slide is slightly out of date. They've just crossed 10 million miles, I believe. And earlier this year in Phoenix, Arizona, normally when they're driving these cars, they have a safety driver in the front seat ready to take over if the car looks like it's going to do something stupid. In Arizona, we've actually been doing trials with about 100 cars with humans in the back seat and no safety drivers in the front seat, driving around the streets of Phoenix, Arizona. Now, Phoenix is an easier environment than most for self-driving cars for several reasons. So first, it's really hot, so there's no pedestrians. Second, the streets are very wide and spacious. The other drivers are relatively slow, and it never rains. But we're doing testing at about 25 other cities around North America, and this is not some distant, far-off dream. This is actually taking hundreds of cars around, driving people around Phoenix, Arizona. So that's pretty exciting, and this is really going to transform how you think about building cities, right? You're not going to need parking places, perhaps in 20 or 30 years in urban environments, or not nearly as many. You can sort of call a car that's exactly the right size for your next journey to come and fetch you. And I think that's really going to be transformative for our society. Similarly, we have the ability to have robots that can actually learn from their perceptual environment. And so, sorry, I didn't get on the Wi-Fi, so I don't have a video, but there's a video there. But one of the things about vision now working is that it makes it more tenable to actually have learned control for robotics from raw perceptual inputs on the robot, rather than having hand-coded control algorithms, because you can actually have the robot understand what it's doing, see the environment around it, and sense what the right thing to do is. And so in 2015, there was a task of picking up novel objects, and the state of the art for this task was about 65% success rate. And one of the things that our group did to start with in 2016 was assemble a lab of about 10 of these robotic arms, and then use supervised learning to try to pick things up. And so essentially, we got a bunch of bins and filled them with variety packs of tools and toys that we bought on Amazon, and then try to have the robot essentially try to pick things up. And a great thing about grasping is that it can be self-supervised. So if I try to grasp something and I succeed, my gripper doesn't close all the way. And if I try to pick up something and I fail, my gripper closes all the way, and I can see that there's nothing in my hand, or my gripper. And by using that, and then pooling the data and experience from these robots, and then training new models every night using their pooled experience, we're actually able to get to a 78% grasp success rate using quite a number of grasp attempts. So about 700,000 or 800,000 grasping attempts improve this state-of-the-art substantially. And then in the 2 years since, we've actually been using more sophisticated reinforcement learning algorithms that allow us to get to much better grasping success rates. And we're now at 96% grasping success rate for novel unseen objects. So the objects we're trying to grasp here are not ones that we were trained on, but they're sort of similar objects, but of the same rough size and form factor, but not ones that we've ever seen and tried to grasp. And so now we're at 96% grasping success rate. And this is a pretty substantial improvement. If you're trying to get robots to do things in the real world, the difference between 65% and close to 100% is a really fundamental difference. In order to really do anything, being able to reliably pick something up is a basic building block that's really important. The other thing we've been working on in the robotics field is how can we actually instill robots with the ability to emulate behaviors that they're seeing as a way of learning new behaviors. So this is one of our AI residents that we have do interesting research tasks. No, I'm just kidding. They do fantastic research, but they also generate training videos for robots, where you can see that this simulated robot is trying to emulate the behavior it sees from the raw pixels in the video. And then on the right, what you see is a robot taking about 10 or 15 short video clips like this of humans pouring liquids into different kinds of cups, from a variety of different angles, and then using a few trials to try to emulate that behavior. So in about 15 minutes, with 15 video clips and about 10 trials, the system is able to learn a pouring policy that is that effective. I would call it four-year-old human effective rather than an 8-year-old human effective. But that's a pretty different way of thinking about how do you give a robot new skills. Because if you imagine hand coding a pouring control algorithm, that's a super complicated task. Like, how would you describe the set of motor commands to give to a robot that would work for pouring and would also generalize to different kinds of cups, different sort of heights of cups, and so on. But being able to observe these kinds of behaviors and emulate them is a really important skill. And you can imagine training data available on YouTube of humans doing lots of different things you might want a robot to do would be pretty helpful. Like, can you flip a pancake, or can you open a fridge door? All these kinds of things are going to be really useful as training data. OK. Another one of these grand challenges was advanced health informatics. And I think there's tremendous potential for the use of machine learning to really improve healthcare outcomes and decisions that are made in healthcare. One area is in various medical imaging problems, because it's obvious now that sort of computer vision has made great strides. Many medical problems are related to medical imaging related sort of analyses. And one of the areas we've been doing work in for the longest, for about 3 or 4 years, is how do we do diagnosis of diabetic retinopathy, which is the fastest growing cause of blindness in the world. And it's, in particular, the way you want to make sure that people don't develop vision loss as a result of this disease is by doing regular screening. Really, if you're at risk for diabetic retinopathy, if you have diabetes, you want to get screened about once a year. So an ophthalmologist would then take a picture of the back of your retina. It looks like this. And then they would essentially try to assess are there symptoms of diabetic retinopathy. And this disease is actually very treatable. So if you catch this in time, there's a simple set of treatments that are available that cure the disease. But if you don't catch it in time, people will suffer vision loss. And in particular in India, for example, there's a shortage of more than 100,000 eye doctors. And as a result, you can't even have enough people screened. And so 45% of patients suffer some sort of vision loss before they're actually diagnosed with this disease. And the way it's diagnosed is a ophthalmologist will look at one of these images and decide on a 5-point scale what level of diabetic retinopathy do they see: none, mild, moderate, severe, and proliferative. And they're looking for things like these hemorrhages here. And if you ask two ophthalmologists to grade the same image, they actually agree on this 1, 2, 3, 4, or 5 number 60% of the time. And if you ask the same ophthalmologist to grade the same image a few hours apart, they agree 65% of the time. Which is slightly scary because the difference between a 2 and a 3 is, go away and come back next year versus we better get you in the clinic next week. But regardless, it turns out you can use general purpose computer vision models, and instead of training them on pictures of dogs and cats and so on, you can train them on retinal images and ratings that human ophthalmologists have given to those images. And by doing that, you can actually get a model. So this was kind of the first paper we published in this space, where we basically showed that by getting each image labeled by 7 board-certified ophthalmologists, and that helps reduce the variance, because if 5 of them say it's a 2, 2 of them say it's a 3, it's probably more like a 2 than a 3. We actually have a model that's on par or slightly better than the average board-certified ophthalmologist at this task, which is great. It turns out you might want to have even a better model. And so there's a subfield of ophthalmology called retinal specialists that actually have more training in assessing this kind of disease. And so if you instead get your data labeled by retinal specialists and change the way you label the data, so instead of getting independent assessments, you instead lock 3 retinal specialists in a room and say, OK, what do you think about this image? And make them come up with a decision. It's called an adjudicated protocol. Then you can actually then train a model that is on par with retinal specialists rather than board-certified ophthalmologists. And that's a higher standard of care, and that's actually what you would want for anyone being assessed for diabetic retinopathy, which is really cool because we now have the ability to take the skills of a retinal specialist and turn that into a model that we can then use for screening all over the world. But the other interesting thing is the things I've described so far are things that ophthalmologists know how to do. So this is a bit of a tale of scientific discovery. So we had a new person join the diabetic retinopathy team, the ophthalmology team. And in order to get familiar with our sort of machine learning pipeline running code, Lily Peng, who runs that team, said, why don't you take this data, and we actually have some images where we know both the age and the biological sex of the owner of the eye. And why don't you try to train a model that can predict age and gender and biological sex from these images? And ophthalmologists don't actually know how to predict biological sex from one of these images. So it should be no better than a coin flip. And so the person went off, and they fiddled with some stuff. And a week later, they came back, and they said, OK, I've gotten my model working. Everything seems to be working. And my AUC for biological sex is 0.7. And Lily said, oh, that can't be right. It should be 0.5. Go away and come back when you've checked everything. And so they went away, and they fiddled with some stuff. And they came back, and they said, OK, my AUC is 0.85. So that got people interested. And it turns out with a bit more fiddling, you can actually then predict biological sex with 0.97 accuracy.
They have to be symptomatic for this to work?
No, this is just a general image. There's nothing to do with diabetic retinopathy. So that got people interested in what else might we be able to predict from these retinal images. And it turns out you can actually predict quite a lot of different things, many of which are correlated with cardiovascular risk. And so it turns out that if you combine these kinds of predictions, you can now get a new biomarker that is essentially a prediction of your cardiovascular risk using just a retinal image that is on par in terms of accuracy with a much more invasive blood test where you'd have to draw blood, send it off to the lab, wait 24 hours, get the lab test results back. And so this might be something that could form the foundation of a new kind of biomarker that you collect as part of a general office visit. And so a bunch of people got excited about this, particularly people who know more than I do for sure. So Eric Topol is a well-known physician, and the Nature Biomedical Engineering news and views associated with the paper had a nice write-up by some eye doctors in Singapore. And they said the information on the retinal image can be used for the prediction of a person's gender is surprising and puzzling. And this guy, who's a well-known ophthalmologist in the UK, says jaw-dropping. So this is pretty interesting for ophthalmology folks. The other kind of area in healthcare that I think is particularly interesting is can we help doctors make decisions that are better using data? And so essentially a lot of what a physician is trying to do is predict the future for a patient and understand if I were to treat the patient this way, what will happen? If I were to try to treat them this way, what will happen? And so on. So given electronic medical record data, can we actually use that to train systems that can help doctors make these sorts of predictions? And a lot of the work in deep learning recently has been focused on what kinds of sequential prediction models are going to be effective. And so in our group in 2014, there was a paper published on sequence-to-sequence learning. So conditioned on one sequence, can we predict an output sequence? This is the result of that translation model that I showed you uses a sequence-to-sequence approach. So conditioned on this English sentence, what should the corresponding French sequence of words that I want to predict be? We actually use this in Gmail to help predict replies for email messages that you've just received. So conditioned on the email message you just received, hi, can you come over for dinner on Tuesday? We can predict what responses might make sense. Sure, I'd love to, what can I bring? Or sorry, I can't make it. And we can also use this for machine translation, as I mentioned. But can we also use this in a medical context? So basically, given a corpus of de-identified medical records, can we line up all the medical events for a patient and treat that as a sequence? And then instead of having one sequence to another, can we take a prefix of that sequence and predict the rest of it? Or take a prefix of that and predict some high-level attributes of the rest of it? Will this patient be readmitted to the hospital if I release them now? What are the most likely diagnoses I want to make for this patient, given the symptoms they're reporting, plus their previous medical history, and so on. And we're collaborating with several different healthcare organizations, UCSF, Stanford, University of Chicago. And we've published a paper on this. And I'll take you through just one of the kinds of predictions that we made in this paper, which is essentially trying to assess the mortality risk of a patient. What is the risk this patient is in the immediate future? This is something that hospitals already do. They assess mortality risks, so that gives them a sense of which patients they really need to pay medical attention to right now because they're at severe risk. And they already have models that they use for this that take essentially 15 or 20 hand-coded variables and you plug it into a formula and you get a prediction of mortality risk. And that's what that dotted line is, shown at different times relative to admission for the patient. And what you see is that using all the data in the medical record, 150,000 data points on average, you actually get a much more accurate assessment of mortality risk to the point where you actually get the same level of accuracy 24 hours earlier for a given patient. That essentially gives you more time as a physician to really focus on which patients are really at risk and need your attention. OK, another of the grand challenges was engineer better medicines. And a bunch of the other grand challenges were all kind of related to understanding properties of either molecules or materials. And we've been doing a bit of work in collaboration with some quantum chemists to essentially work on this problem of predicting different properties of molecules. And so one of the things a quantum chemist wants to do is take a configuration of molecules and then understand certain things about that configuration. You know, does it bind with this or that? What are its quantum properties? Is it toxic? And one of the ways they do that is they have a traditional kind of high-performance computing style simulator for these molecule configurations that can give you the answers to these questions if you plug it in and then wait a while. So in about an hour, you can get an answer to these kinds of questions for a single configuration. Now it turns out you can use that simulator as a teacher for a machine learning model. So given a bunch of inputs and outputs, you can essentially learn how to perform the same kinds of computation that the simulator is doing, or to approximate the behavior of the simulator to the level that you can actually not tell the difference in accuracy between the machine learned model and the original simulator. And the key advantage of doing this is that the system is then much, much faster. So in particular, it's about 300,000 times faster, and you can't tell the difference in accuracy. And that really changes the style of chemistry you do, because if your tools suddenly get 300,000 times faster, that means that it's completely feasible to start a job to screen 100 million molecules while you go make coffee. You come back, and then you can kind of identify the 10,000 most interesting things and kind of focus on those. Whereas before, that was completely infeasible. This general pattern of having a really expensive simulator written in a more traditional HPC style and then training a machine learning model is not just for chemistry. We've actually seen this behavior in other domains as well, including earthquake fault simulation, where you have kind of a physics-based model for earthquakes, and you can then train a machine learning model to approximate the behavior of that more expensive simulator. So one of the vaguest of these grand challenges, I think it was kind of thrown in as a catch-all, was to engineer the tools of scientific discovery. And it's clear that if machine learning is going to be sort of an important component of how we're going to make progress on some of these other grand challenges, that we should focus on building tools that enable us to express machine learning computations in a way that is sort of flexible and easy and allows us to then use those machine learning computations in a variety of places. So our group has actually been focused on building machine learning oriented tools for quite a while. And TensorFlow is kind of the second generation of a system that we've built for expressing machine learning computations for our own research and also for Google production uses. And we decided we would open source this version, which was then, we released the first version as an open source release in the end of 2015. And one of the key pieces of abstraction in TensorFlow is that you can define a computation as a graph structure that is defined in a high-level language, and then that graph can then be compiled and optimized and mapped onto a bunch of different kinds of computational platforms. It can run on CPUs or on GPUs or on tensor processing units, which I'll talk about in a minute. And the nodes in this graph represent different computations and state, and the data flowing along the edges are tensors, sort of multidimensional arrays. And eager mode essentially makes graphs in this system implicit rather than explicit. And so TensorFlow has been reasonably successful in getting adoption and interest in the open source community. And so this is one measure of interest for different open source repositories that are focused on machine learning, which is a measure people can star GitHub repositories they're interested in using. And you see TensorFlow there in the purple compared to a bunch of other open source machine learning packages. And one of the things we hoped would actually emerge by open sourcing this is that we would then be able to have many people outside Google also work on improving this general system and improving it in ways that allow it to run in a wide variety of different systems, that people will then sort of release example machine learning models for a variety of tasks expressed in TensorFlow and so on. And so that's been quite gratifying to see. And people have done all kinds of interesting things with it. So there's a company in the Netherlands that, for example, makes fitness sensors for cows. And if you have a herd of dairy cows, it's actually kind of hard to tell which ones are feeling a little sick or behaving badly or interestingly today. And so by taking the data that these fitness sensors collect and then analyzing it with TensorFlow, they're able to actually discern which cows are is Bessie number 12 not feeling so good today, or 14, I guess. There's another collaboration that we had nothing to do with between Penn State and the International Institute of Tropical Agriculture in Tanzania, where they've been building machine learning models that actually run completely on device. So in the middle of a cassava field in Tanzania with no network connectivity, they're actually able to take a model that uses the camera as input, and you can take a picture of a cassava plant in your field and understand, is that cassava plant diseased? And if so, what disease does it have and how should you treat it? And this is an example of, now that computer vision works, we actually want to run machine learning models in many, many places in the world, not all of which are data centers, many of which are sort of on-device models without network connectivity, where you actually want a reasonably an accurate model to be able to run on the sort of computational power of something like a phone. OK, so for the last bit, I'm going to talk about some different pieces of work and then how I think they might all fit together in a sort of interesting future sort of path. So one thing I think we want is, right now, a lot of the machine learning models we train are essentially large computational graphs where we sort of fully activate the entire model for every example. So we do every single last floating point multiply and addition in order to make some sort of prediction in a task we care about. But that's a bit unrealistic, right? If we imagine large models, we may want to have different parts of the model that are good at different things and only activate parts of the model that make sense for a given example. Right. So one of the things we've been working on are what we call sparsely gated mixtures of experts. So if you imagine a traditional machine learning model, deep neural net, with sort of a bunch of layers shown in pink here, one of the things we might want to be able to do is add these mixtures of experts, where every expert has a lot of parameters that we can use to remember a lot of stuff from the training data, and have many of those experts, thousands of them perhaps, and where we actually learn this gating network. So that gating network can also be learned. So we can learn which experts are good at which kinds of things. And sometimes we might send it to just one expert. Sometimes we can send it to 2 or 3, and then use the sort of gradient that comes back to actually train the gating network. So we can then learn which of the experts was better at that particular example, and then make it more likely that we send examples that this expert will be good at to the expert that actually has that expertise. And so in a language modeling context, you can actually see that these experts really do get different kinds of expertise. So for example, here's the kinds of examples that are routed to 3 different experts in this model. And you can see that expert 381 is really good when the context involves innovation in science and research. Expert 752 here is really good at playing a leading or critical role. And expert 2004 is kind of good at fast adverb-y things. And by having all those different pieces of expertise, if you compare this to a system without the mixture of experts, so this is for a language translation task. And we care about several of these different measures. So one is the BLUE score, which is a measure of translation quality. And the bottom row here is the production Google Translate system. And the top row is that system augmented with these mixture of experts layers. And so you see we get about a 1 blue point improvement, which is pretty significant in terms of translation quality. But we also get a reduction in training time of about only a factor of 10. So 6 days on 96 GPUs versus 1 day on 64 GPUs. And we're able to reduce the size of the pink layers in the mixture of experts approach because it has all this capacity in the actual experts. So we can reduce the size of the model, of the part of the model that is not sort of this sparsely gated portion. And so therefore, the actual cost in computation per word at inference time is only about half the cost of the larger model.
So is an expert a human being, or is an expert
No.
a piece of software?
An expert is, you can think of as just a large matrix of parameters. So it's essentially another small mini neural net, and you learn to route to this mini neural net. OK. Another area we're particularly excited about is how can we automate a lot of the kinds of decision making that a human machine learning expert makes when they're trying to actually solve a new problem. So the current way you solve a machine learning problem is you have some data set you care about, you have some computational devices, maybe a bunch of GPU cards in your desktop machine or some cloud-based devices, and then you have a human machine learning expert sit down and make a bunch of decisions about how to solve that machine learning problem. What kind of model structure should I use? What learning rate should I use? Should my model have 19 layers or 15 layers? Should it have 3x3 convolutional filters or 5x5, and so on. So can we turn this into something that looks more like an automated system that uses data and perhaps much more computation to do the kinds of experimentation that a human machine learning expert either might do experimentally or use their own intuition from solving other problems to actually solve? And so one of the first pieces of work our group published in this space was in a piece of work called neural architecture search. So one of the decisions the human machine learning expert makes is what neural architecture should they use for modeling this particular problem. And so the idea here is we're going to have a model generating model. And we're going to use reinforcement learning to train the model generating model so that it generates better and better models. So basically, the inner loop of this looks like generate 10 models, train them all for a few hours on the end problem you actually care about, and then use the loss of the generated models, the accuracy of those models, as a reinforcement learning signal for the model generating model. So you can essentially steer it away from the part of the space of models that didn't work very well and towards this part of the space of models that work pretty well. And then you're going to repeat. So quite a lot of times. So we're going to repeat many, many times. And eventually, we get more and more accurate models using this approach. And they look a little bit strange. Like a human machine learning expert would probably not sit down and design this particular model structure. But this is one of the more accurate models that the system came up with for a particular computer vision problem. Interestingly, it has some characteristics of things that we know that human machine learning model experts actually have found useful in computer vision problems, which is the notion of skip connections. So the ResNet paper by Kai-Ming He and others essentially has a structured variety of these skip connections where you have every layer, there's a connection that skips that layer or goes through that layer. And so that's a much more structured version of these long-range skip connections. But the essential intuition is you want to create pathways that allow data to flow much more directly from the input to the output. And those skip connections that skip many layers of computation essentially allow you to do that. And so let's look at how well this works. So on this graph, I'm showing on the x-axis the number of multiply-add operations for a model to make a prediction for a given image. And generally what you see, and on the y-axis is accuracy. And so what you see is generally as you apply more computation, you get more accuracy, which is good. And each one of these black dots is an interesting research paper that was published that advanced the state of the art in this particular problem. And so each one of those typically represents 5 or 6 co-authors working together for 6 months or a year to produce some really interesting result. And if you apply AutoML to this problem, you actually do reasonably well. So in particular, you actually can produce models that are higher accuracy when you don't care about computational cost. So they're actually a little bit more accurate and significantly less cost. And at the low end, where you care maybe about a model that might be very flexible and easy to run on a mobile phone where you don't have much computation, you can actually get a more accurate model for the same amount of computational cost. So this is, I think, an indication that this kind of approach of searching large computational spaces for what are the best approaches to doing machine learning models is quite real. It's not something that humans necessarily have great intuitions about, and we should allow machines to do this sort of search. We've actually released this as a product in our cloud offerings for a lot of companies have computer vision problems for their own particular problem. Maybe it's like a factory assembly line where they want to be able to identify a particular kind of part in their company, and they want to get a highly accurate model. And here they can do that without necessarily needing a lot of machine learning expertise on their own. There's a whole suite of follow-on work in this general space. So for example, we've been exploring the use of evolutionary algorithms rather than reinforcement learning algorithms for generating these kinds of model structures. We can actually learn optimization update rules symbolically, or learn nonlinearity functions that seem more effective than the traditional ones that most people have been using. We can incorporate both the actual computational cost of the model plus accuracy into the reward function for the architectural search, so that we can say, I really want a model that runs in 20 milliseconds. So search over the space of models that are 20 milliseconds or less, and find me the best model given those constraints. You can actually learn data augmentation policies. So a lot of these machine learning models use a set of transformations of the original input data. So they might take an image, resize it, pick a random crop from it, maybe flip it horizontally half the time. Those pipelines generally are human generated. It turns out you can search over the space of sequences of image transformations in the same way you search over the space of architectures and find sequences of image transformations that improve the overall accuracy of the end resulting model without sort of hand coding exactly the set of transformations you want to use. OK, but if we're going to have these sorts of approaches that require running large computational searches, essentially wrapping another loop around the machine learning training process, we're going to need more computational power. And so deep learning models actually are really changing how we think about designing computers. And they have two really nice properties. So all the algorithms I've described and models I've described to you have these two amazing properties. So one is that they're perfectly tolerant of very reduced precision. So you can carry out all the computations in these models to roughly 1 decimal digit of precision rather than 6 or 7 digits. And that means that you can essentially, in the same amount of chip area, get many more multipliers and adders for reduced precision computations than you could for much higher precision ones. And the other property they have is that they're all compositions of a handful of different operations composed in different orders. Essentially, low precision linear algebra. So different kinds of linear algebra operations, matrix multiplies, vector dot products, and so on. So if you can build machines that are really good at low precision linear algebra and nothing else, that's actually the kind of machine you actually want for running machine learning algorithms on. And so we actually started thinking about this in about 2012. When we were starting to see initial success in some of the speech recognition and computer vision problems that we were working on at Google. And in particular, we saw significant reductions in the error rate of our speech recognition system when we used a deep neural net for the acoustic model rather than the earlier machine learning model we were using. But that was much more computationally intensive than that earlier model. And so we started to get a bit worried where, what if 100 million of our users suddenly started talking to their phones for 3 minutes a day? We have about 1 billion users, so maybe 10% of them might start dictating emails, or who knows what, if the word error rate is significantly better. And running speech models on CPUs, which is all we had in our data centers at that time, we'd have to double the number of computers that Google had just to support that speech recognition model, let alone all the other things we do. And that's a little troublesome. Even if it was sort of cost effective, it still takes a long time to double the number of computers Google has, because you have to actually pour concrete for new data centers, engage wind farms to give you power contracts, install computers, and so on. So we started to think about what kind of hardware we could build that would take advantage of those two properties that I showed you. And we first tackled the problem of inference, rather than training. So where you already have a trained model and you just want to apply it for things like speech recognition or vision. And so TPU v1 is a tensor processing unit. And these systems have been in production use for about 4 years. They're used in every Google search query. They're used for the machine translation system, for speech, for image recognition. Our DeepMind colleagues used actually these 2 racks of tensor processing units for the AlphaGo match that they did against Lee Sedol in Korea. You can see the little Go board that I helped paste to the side of these things in the data center in Iowa. The reason we did inference first is that it's a much simpler problem than training. But then we decided to tackle the problem of how do you build accelerators for training. And the reason training is more difficult is inference, you can generally get a model to fit on a single chip. And so it's really like designing a card that can go into a computer. Training, you're never going to get enough compute on a single chip to train all the problems you care about. Because if you did, you'd just care about bigger problems. And so really, you then start to have to think about entire systems. How do these chips then connect together in a way that allows you to effectively use lots and lots of these chips to train a single computer, to train a single problem. But if we peek inside one of these chips, it's actually a reasonably simple architectural design. It basically has a really large matrix multiply unit. Every clock cycle, you can do 128 by 128 matrix multiply. It has some scalar and vector units for things that aren't matrix multiplies. And then it has high bandwidth memory to sort of feed all these things and get them back. And they're designed to be connected together into these larger configurations that we call pods. So essentially, there's a collection of these boards. They're grouped together in a 2D torus. And one of these second generation systems has about 11.5 petaflops of compute. The next generation, a year later, is essentially roughly the same design, but with some tweaks and also liquid cooling. So we actually have water flowing through those tubes, which is somewhat exciting next to your processor. I'm told we haven't had too many leaks, which is good. And those are designed as well to be connected together into large pods. And the pod scale is increased in this design. So one of these pods is about a little bit more than 100 petaflops of compute of reduced precision arithmetic. So to put that in perspective, the #1 supercomputer in the world, actually I don't know the current stats, but as of 2 or 3 months ago, the #1 supercomputer in the world was about 125 petaflops of double precision arithmetic. So it's not quite apples to oranges, but this is sort of roughly in that ballpark in terms of number of operations per second. And they're programmed via TensorFlow, so the same program runs with minor modifications on a variety of these different platforms, and also the same program scales via synchronous data parallelism without modification on everything from one of these boards up to a full-size pod. And we've been making these TPUs available to researchers who have interesting machine learning problems that they're willing to publish openly about. So we have a program that makes these available for free for people who have sort of interesting computational needs and are willing to do that. In particular, for this audience, we'd like to make these available for your own machine learning research. So we'd like to offer people, if they want, 5 of these TPUs plus a bunch of preemptible ones. And you can email that email address and mention this talk. So we think people will like those. And I will go on. Or you can try them right in your browser right now. You can start with hello TPU, and you can try Keras models on top of that. And Collab is this kind of interactive programming environment that shows up in a browser tab and allows you to sort of interactively intermix sort of code and then visualizations of different kinds of things. So it shows up kind of like this, combines text and code and the output of that code in an interactive collaborative document. We think a lot of people at Google have been using this internally for their own work. We think it's pretty interesting. OK. One of the other things that we've been looking at is what is the effect of data parallelism on neural network training. In particular, when you do essentially take a model and make many replicas of it, and then train larger batches where each of these replicas gets one slice of the batch, that gets you substantially far in terms of scaling. But we were interested in how far that scaling exists. And some of my colleagues recently published a paper they've been internally calling batch science, that has been looking at measuring the effects of data parallelism on neural network training. And they took a whole bunch of different problems and a whole bunch of configurations of different kinds of optimizers and looked at what are the effects of batch size on the number of steps of batches of that size to get the model to converge to different levels. And what you see is that, for example, if we look here, there's generally, for every problem, there's this perfect scaling region where you can increase the batch size and get perfect scaling in terms of a reduction in the number of steps corresponding to the amount of increase you've given to the batch size. And then there's a period of diminishing returns where things kind of flatten out. And you can still get some benefit, but it's not proportional to the amount of improvement you've made. And then there's a period of maximal data parallelism where beyond that, it doesn't make sense to increase the batch size. And so that has implications for what are the largest size problems you can train on these large pods. Particularly, it means that I think we'll need models that are both model parallel, where you have a single model spread over many chips, and then have many replicas of that model spread out over something like a very large pod, rather than a single model on one chip. OK, so let me close with how some of these ideas fit together. I think we're going to want large models, sparsely activated, single models that solve many different tasks rather than training separate models for every task that we care about. And we're going to want to dynamically learn interesting pathways through this large model that solves many different problems. One of the big impediments to making progress in machine learning today, I think, is we tend to focus on training models for one thing and then train a completely different model on a different task we might care about. And we really want to be able to take advantage of commonalities across these different problems. So if you imagine a cartoonish diagram of what this might look like, we have a bunch of tasks colored different colors here. And maybe we've learned a bunch of pathways through this large model that is sparsely activated. And so some pathways are good for certain kinds of tasks. Other pathways are good for other kinds of tasks, similar to the mixture of experts work that I described earlier. And now we have a new task. All right, so now in the same style as architectural search, but changed a bit, we can now imagine doing a pathway search for what pathways are effective for this new task through this model. And maybe we'll find that this pathway is a particularly good one for this new task and gives us a pretty good result for the data we have available. And maybe we'll decide that we want to make this particular pathway more accurate for this task and introduce a new component in this system that allows us to sort of specialize for that particular task. I think, and then that component then becomes available for future tasks and can also be leveraged as part of training other tasks. So I think this is kind of an interesting direction to be thinking about for training large-scale machine learning models. And the final thing I'll say is there are lots and lots of implications of this kind of work for how we deploy these kinds of models in a variety of different kinds of ways throughout society. One of the things we've been thinking about internally at Google, and we published externally in June, a set of principles by which we think about machine learning models and AI and how it should really be used in our products. And also, we're publishing this so that other people can benefit from our own internal thinking. And I think this is a good set of principles by which to approach using machine learning. And in particular, I'd like to point out that these are, in many cases, active areas of research. So for example, if you look at number 2 there, avoid creating or reinforcing unfair bias, that's actually an active area of research that we've been doing quite a lot of work in the last 2 or 3 years, where the state of our understanding is advancing, but our goal is to use the best understanding we have for applying these models into our products and our uses, but also to advance our field of understanding for these things so that we sort of can make progress on better understanding and also sort of applying these in a principled way. And with that, I'm done. Thank you very much. I think, thank you all for listening.
Okay, that was breathtaking. Thank you very much. And I'd like to open it up for questions, if someone wants to step forward. And if not, I will ask the first question. This has been terrific, and one has the feeling that in a new technology like this, that you first go after the low-hanging fruit. Shall we assume that the best things have already been pursued, and that maybe as we look to the future, we'll have like problems of diminishing importance, or is this just going to get bigger and bigger as time goes by and we get more powerful? What's your opinion?
Right. I mean, I think obviously the field of AI in general has gone through like periods of hype and excitement and then kind of disillusionment. I do feel this time is a little bit different because we've made significant progress on actually fundamental basic problems in, for example, computer vision and speech recognition. And if you look at all the places that you might want to use computer vision now that it works well enough for applying it to different problems, even if we made no further research progress, just getting the use of computer vision out into all the places that it makes sense to use will actually take quite a lot of time. And I also don't think we will stop making progress completely. And so I think we will continue to make further research progress, but also you'll see more and more applications of this kind of work.
Well, that's a very conservative assessment, if you don't mind my saying so. Okay. Let's see how we're doing with more questions. Seems like the students are particularly quiet. Oh, there's one.
One of the things that you mentioned in those design principles was commitment to privacy, but whenever you're designing these deep learning systems, you need a lot of data to kind of train these things. How do you think in the future we're going to negotiate that difference between this huge demand for large amounts of data from people and the need to maintain privacy concerns, I guess, from your perspective?
Yeah, I didn't talk about it too much, but there's actually a whole emerging research area of how do you actually learn on private data in a way that you can actually get characteristics of that data into machine learned models without actually bringing all the data together. That's an important research area, I think, particularly in the field of healthcare. There's good examples of why you might want to be able to do that. You might want to be able to, for example, learn across different healthcare systems, particularly for sort of rare conditions. An individual healthcare system may not have seen very many patients with a particular disease, but across many healthcare systems, you may have more statistical power in that, but you don't it's obviously implausible to combine all that data together. So I think that's definitely an interesting area. And the other thing I would hope is that if you were to build a model like this, and imagine millions of different things that model knows how to do, that when the million and first thing comes along, you actually would need much less data for a new problem than you need from the approach we use today, which is essentially start with random floating point numbers, learn everything about this problem from a large number of examples for that problem. If you could get this to the point where you now need hundreds of examples, not tens of thousands, for a new problem, that actually may make it easier to learn new tasks by sort of learning and generalizing across different tasks.
So does this diagram give us hope that we now do learning in a way that the machine could actually explain how it masters a particular task? And so that when we go from learning how to play Pong in one particular orientation, and if we turn the screen 90 degrees, it doesn't have to start from scratch, but it learns higher level internal primitives that you can reuse then.
Yeah, I mean, I think that the interpretability of the model is somewhat independent of this sort of approach for doing heavily multitask learning, but the interpretability of models is very important for certain kinds of of tasks. And there's actually a whole active field of research of how do you make what are normally thought of as sort of black box style models actually be more gray box rather than black. And there's actually quite a fair amount of work in the last few years that has actually gotten, particularly for computer vision problems or sort of sequential attention-based models, that can actually make these models more explainable. Why are they making a particular kind of prediction? It's because they see this kind of thing in this image, or they focused on this particular phrase in a medical note in order to say, the patient might need a heart valve replacement. So that's an important area. I didn't really touch on it in this talk, but it's important.
Just to follow up back on this slide. So my interpretation of this slide is that I could take your TPU pod that was used to do the Go challenge and turn it around and get it to be a super player or another 3-dimensional or 2-dimensional board game. Is that the proper interpretation? Like the World Chess Championship just finished, so can I take your pod of TPUs used to challenge Go to again Go challenge for chess or 3-dimensional checkers or whatever?
So I think the way I've been thinking about this is, suppose you had a whole bunch of supervised learning problems, and you wanted to train a single model to tackle all of them rather than separate models to tackle each one individually. And to the extent that you had sort of reinforcement-based learning and there was generalization to be had across those different games, that would be the hope. This is sort of an early idea of where we might want to go, not a finished concept. So it remains to be seen. Yeah.
Can you go back to the Cloud TPU email?
Oh, sure. I would be happy to. This one? Yes. Sure.
Just wants to look at it.
It's so beautiful.
Say the email address.
Yeah, tfrc-support@google.com.
While you have that up, can you talk a bit about the memory? As you make these models really big, you're going to have, it's not just compute you have to deal with, there's a lot of memory, the model state, the gradients, and so on.
Yes.
How's the TPU going to look when we change our model architectures to be massive?
Okay,
will we use the same TPU, or will we build different ones?
Right.
So, the microphone to him on top.
Yeah, that's fine. So I will repeat the question. So, so if you look, sorry, I'm going to go here. So each one of these chips has 16 gigabytes of memory. So there's 64 gigabytes of memory on that board. And basically, to the extent that your model fits in a 16 gigabyte footprint, you can just use data parallelism. Right. But obviously, you can also use model parallelism, where the general approach for model parallelism works when the network interconnects between those chips are very high speed. And so we've actually designed this to have very high speed interconnects. And so that means you can, for example, take a, say, 4x4 tiling of 16 chips, make that one model, and then use data parallelism across those groups of 16 chips to then get both a combination of data and model parallelism.
I guess, will the bottleneck shift from compute to network in the process of changing our architecture?
It depends tremendously on the style of model you have and the ratio of compute to network. If you look, one of my colleagues, Noam Shazir, and others have developed a programming model for this kind of approach called Mesh TensorFlow. So if you look at that, that's a pretty nice expressive way of expressing model parallel computations in a way that maps well onto these kinds of computers.
I wonder if I can ask a question about bias that came up toward the end of your presentation.
Sure.
It seems to me that we're looking at statistical analysis of things that are going on in society. For example, I heard an application for predicting where crimes would be in Los Angeles, which is kind of not your typical machine learning application, but it's out there. The machine learning, we often don't know where it's going, and let's say it ends up with something that maybe you don't like, and you say, well, I wasn't biased. It's just the machine learning did this. I'm a very fair person. So how do you actually deal with this?
Right. So I mean, I think the general problem is that often the way we train these models is we train on the data that we collect from the world as it is, not necessarily the world as we would like it to be, right? And the first step is realizing that that may be the case. And for example, Moritz Hart and others, when Moritz was visiting Google, let's see, did some very nice work. For example, this paper on equality of opportunity in supervised learning is actually a pretty nice approach where you can essentially take any machine learning model, wrap the output of it in some adjustments that you can make algorithmically to ensure that different subpopulations have equal chances of acquiring a certain outcome, all other things being equal. And so there's a pretty nice result in that work. And that's just one example of ways that you can algorithmically unbias even if your underlying training data is biased. But it's a complicated problem, and the thread of research here indicates this is not a solved problem for sure.
Anyway, this has been a fantastic lecture. I want to invite Jeff again next year and hear about the progress. But in the meantime, let's give him a rousing round of applause.
Thank you.